Let's talk about a revolution. Not one happening in the streets, but one that's happening deep inside the technology we use every single day. We're going to dive into how artificial intelligence is no longer just a ghost in the machine. It's now becoming the architect of the machine itself.
I mean, just let that sink in for a second. It's a pretty wild idea, isn't it? But look, this isn't some far-off sci-fi concept. This is happening right now. AI is starting to close the loop on itself, designing the very silicon that's going to power its own more powerful descendants.
So, you might be asking, why now? What's changed? Well, the simple answer is that we're running up against the wall. A very, very real physical wall.
For decades, the playbook in chip design was pretty straightforward. Make everything smaller. Smaller transistors meant a faster, more powerful chip. But when your components are only the width of a few dozen atoms, you just can't get any smaller. We've hit the physical limit, and the complexity of designing at that scale is it's become way too much for human engineers to handle all on their own.
To really get a sense of how big this problem is, you have to understand this idea of design space. It's basically the total number of ways you could possibly arrange all the little components on a single chip. For a modern chip, that number is bigger than the number of atoms in the known universe. I mean, think about that for a second. There is no way a human, or even a giant team of humans, could ever explore all those options to find the best one. It's impossible. But for an AI, not so much.
And that's exactly why people are calling this the AlphaGo moment for hardware design. You remember AlphaGo, right? The AI that beat the world's best Go player? It found moves in this ancient game that no human master had ever even considered. Well, AI is doing the same thing right now with chip layouts. It's discovering brilliant, counterintuitive designs that are just flat out more efficient.
So how in the world does it do that? Well, tools like Google's AlphaChip basically turn chip design into a game. The AI plays millions of rounds, using a technique called reinforcement learning to figure out the absolute best place for every single component. And here's the kicker. It's constantly juggling all these competing demands: power, performance, physical size, all at the same time. That's something that's incredibly hard for human teams to do. And the payoff is huge. We're talking about compressing years of painstaking human design work into a matter of weeks.
Okay, so this isn't just about designing these massive, complex chips at a high level. This revolution is also completely changing the day-to-day grind for engineering teams. And it's doing it by borrowing a battle-tested playbook straight from the world of software.
And this slide just says it all, doesn't it? On the left, you've got the old way. And you know what this looks like, right? The folder full of files named design_final, design_final v2, final_final, I swear this is it.zip. It's chaos. People are accidentally overwriting each other's work, and you're stuck in these endless review meetings with giant spreadsheets. But now, look at the right. That's the new way, using software tools like Git to bring some sanity to the process. You've got small, manageable changes. You've got reviews that happen on your own time. And, crucially, you have a perfect history of every single change that was ever made.
But this is where the real magic happens. See, a standard software tool can't really show you the difference between two incredibly complex hardware design files. But new platforms can generate what's called a visual diff. It's super simple. Red is what got taken out, yellow is what's been tweaked, and green is all the new stuff. All of a sudden, everyone on the team, not just the engineers with the super expensive software licenses, can instantly see and understand what's changed. It just blows the whole review process wide open. Okay, so we've talked about big picture chip architecture, and we talked about the team workflow. But what about you, the individual engineer? Well, this is where AI is becoming your personal co-pilot, catching all those tiny but absolutely critical details that, let's be honest, we humans sometimes miss.
65%. Just let that number sink in for a second. What do you think that could possibly represent? It's a pretty stark reminder of just how easy it is for things to slip through the cracks, and how powerful AI can be at catching them.
It turns out, in a huge pilot study, an AI schematic analysis tool called Katie found major errors in over 65% of the designs it looked at. And these weren't just random designs off the street. These had already been reviewed and signed off on by human engineers. We're talking about the kinds of little mistakes that can lead to huge, expensive delays down the line, and the AI caught them before they could do any real damage.
And you might think this is some super complicated process, but it's actually dead simple. First, the engineer just uploads their design files. Then the AI gets to work. It automatically reads the instruction manuals, the data sheets, for every single component on the board and analyzes how they're all connected. And in just a few minutes, or maybe a couple of hours, bam, The engineer gets this detailed, interactive report that flags any potential problems. It's like having a world-class expert looking over your shoulder on demand.
Okay, I know what you might be thinking. With all this talk of automation, is AI coming for the hardware engineer's job? And the answer, from pretty much everyone in the field, is a resounding no. The goal here isn't to replace engineers, it's to give them superpowers.
Think of it this way. The AI is amazing at exploring those billions of design options and spotting tiny mistakes that a human eye might miss. But it absolutely needs a human to set the strategy, to define the goal, to provide the creative spark. It's a tool, a really powerful tool, that frees up engineers from the tedious stuff so they can focus on actual innovation.
So, to get the most out of these tools, there's a really simple 3-step framework to follow. It's super intuitive. First, you, the human expert, define your intent. Then, you step back and let the AI do its thing, all the heavy lifting and number crunching. And finally, you come back in to review the results, use your expert judgment, and give the final sign-off.
But what does defining your intent actually mean when you're designing a circuit board? Well, it's all about setting the rules of the game for the AI. You're the one who tells it the critical electrical rules. You lay out the manufacturing constraints. You group components together into logical blocks. You tell it, hey, these connectors absolutely cannot move. You're providing the creative and strategic framework, and the AI works its magic within those boundaries.
Of course, this all sounds great, but switching to a new way of working is never that easy. And for AI and hardware design, the two biggest roadblocks are usually security and, honestly, just getting people to change how they've always done things. And this is the question on every engineering manager's mind. Your circuit designs, your schematics, that's the crown jewels of your company, your most sensitive intellectual property. Is it really safe to just upload all of that to some third-party service in the cloud?
Well, the companies building these tools know this is a huge deal, and their answer is that security can't be an afterthought. It has to be the absolute foundation of everything they build. You can see here, for instance, how everything is designed in layers to protect that data at every single step of the process, from your computer all the way to their secure servers and back.
And we're not talking about just a password here. We're talking about serious, concrete protections. Things like your design files are only processed in the computer's active memory. They're never actually saved permanently to a hard drive. All the data flying back and forth is encrypted with the latest standards. There's a powerful firewall blocking bad actors. And they even hire outside hackers, the good kind, to constantly try and break in, just to find and fix any potential weak spots.
So once you get past those very real security concerns, the conversation really changes. Suddenly, the risk isn't about trying something new. The real risk is in doing nothing. As this quote puts it, in a field that's moving this fast, if you hesitate, you're not just standing still, you're actively falling behind.
And that really brings us to the big final idea here. For as long as I can remember, there's been this huge divide. Software development is fast, nimble, agile. Hardware development is slow, expensive, and methodical. These new AI tools are finally starting to bridge that gap. So I want to leave you with this question. What does our world look like? What becomes possible when we can finally design and build physical hardware with the same incredible speed and agility that we have with software? The possibilities are, well, they're kind of mind-blowing.